Hello everyone, welcome back to our famous homework where we were trying to verify a theoretically obtained probability on 4 rounds of present. So I already graded your homeworks and I tried to give a few comments about it, but I realized that I have a lot of things to say, so instead of writing a very long email, I decided that it is easier to just record my voice so that we can save the time. So recall that we were trying to implement a simple code where we were giving an input difference alpha, which is written here, and after 4 rounds of encryption we were checking if the output pairs have the difference beta, and just by chance in our example alpha was equal to beta because this was a 4-round iterative differential characteristic. So what you needed to do is just obtain 100 counters, add them and thus divide it by 100 to obtain the average of these values, and from here check what is the practical probability and compare it with the theoretical one, and then we will see if it is if the theory matches the practice, which is most of the time is not the case. So the homework was about this. So in order to do the homework you need to generate an random plain text. And I told you that since the theoretical probability is 2 to the minus 18, n should be larger than 2 to the 18. So first question is, what should be your choice of n? And actually we talked about this a lot. I mean, when you are performing an attack, you are trying to find an optimum n. And in this case, actually you could choose n as large as possible depending on your computational power. But the problem is, none of you gave a justification for your choice of n. I mean, we know that it should be larger than 2 to the 18, but choosing it 2 to the 19 is not a good idea, and a lot of you did this. So what should be n, let's say? So easiest thing it was to do is to perform this experiment with low data like 2 to the 15 and do it as large as like 2 to the 28 to see how the probability changes from time. So as you can see, when you perform this experiment with few data, the probability is this. It's something here. Or if you want to see the logarithm, it is 2 to the minus 17.83. So when you increase the data, perform the same experiment, you realize that now it is really different than this one. So it becomes here. Then goes here and here and here. As you can see, it oscillates and it doesn't converge to a point at this case, right? It's not converging, it is oscillating. So for this reason you have to increase n and see how this oscillation goes, and as you can see at some point it starts to converge here, okay, which is something close to the 2 to the minus 17.89 or 90, something along these lines. So the practical probability you obtain should be inside this margin, let's say. So it should be around here, okay. So as you can imagine, choosing 2 to the 19 is not a good idea because it makes a peak here, or it makes a very low peak here, and so on. So this is why you need to choose it and it's small as 2 to the 22. If you're choosing it less than this number, then it is not a good idea, because a lot of you chose it 2 to the 20, but as you can imagine, this is not a good idea, because since the theoretical probability is 2 to the minus 18, this means that your expected value is this number times 2 to the minus 18, which is 2 to the 2, which is just 4. So if your expected value is 4 for this distinguisher and it is 0 for a random permutation, you are trying to distinguish two different binomial distributions which has very close expected values, 0 and 4. And in our lectures we talk about this a lot. You know, we talk about non-detection and false alarm probabilities. We even calculated them, and in this case you can even calculate by hand what is your false alarm and non-detection probability, and you can easily guess that it is a little bit high. So you shouldn't be choosing n equals to this. But most of the time your experiments give some good results anyway. This is because we are performing this experiment for 100 keys and we are just taking the average of it. If you perform this experiment for a single key, then these probabilities will really oscillate something like here and converge here. So when you are choosing 2 to the 20, actually since we are performing the attack for 100 different keys, it is like performing the experiment for 2 to the 27 data for a single key. So this is why some of you obtain good results even if you are using a small number of data. Okay, and actually be careful about what your choice of n is, because for instance one of the submitters said that they chose n equals to 2 times 10 to the power 19, and this is not possible because this number equals to something like 2 to the 60, and you cannot perform 2 to the 60 present encryptions with your laptop or anything, and this code is written in Python, so it is not possible. You need a supercomputer to perform 2 to the 60 encryption operations for a Python code. Okay, so just be careful about what you are doing. Okay, so this actually tells what should be n is. So since most of you chose n equals to 2 to the 22, I performed the experiment with this many data and obtained counters for 100 keys, as you can see here. So why are we doing this? Because since the theoretical probability is 2 to the minus 18, and if you are using 2 to the 22 data, this means that your expected value is what? 2 to the 4, which is 16. So expected value is 16, and as you can see, these numbers are oscillating close to 16, right? I'm showing you these results because, as you can see, there are no zeros in these counters. All of the keys get sometimes small values like 7, but sometimes high numbers like 32 or even 35 here. But the average becomes the total sum is this. When you divide it by 100, you will see that average is 17.26, and the probability is this. And when you do the logarithm in base 2, you will obtain that something like 2 to the minus 17.90 something. So I'm showing you these results because I have received some homeworks where people performing this experiment and using this many data obtain a lot of zero counters here and sometimes a high value here like 100 and a lot of zeros again. So this means that there is something definitely wrong with your implementation. Okay, just try to find it and correct it. You cannot, statistically speaking, you cannot obtain such a result with this many data. So either there's an implementation error, and this can be due to your key XOR or key schedule algorithm. You are doing something wrong there because choice of keys should not have this kind of effects. Okay, so try to find that. And sometimes maybe your random number generator is not generating numbers in a correct way. Maybe it goes into a loop, so you are generating the same data over and over again, and so if you don't get a counter, then you don't get a counter for all of them or something like that. But there is definitely something with your code and you have to correct it before moving on. Okay, and some of you said that they couldn't finalize the homework because even though they think that their implementation is correct, when they run this kind of experiment, what they all see is all zeros here. All of the key counters are 0. So this means that again there is a implementation error, and some of you asked me to check your code and find that error, but you know it is hard to find bugs in other crypto implementations, and even if this is just a one page of code, it is not that easy to find where the fault lies. So this is what I was trying to actually teach you all these years. You cannot get a crypto implementation from somebody else and think that you are secure. Okay, there's no point of doing that. You cannot trust an open source because you cannot even find your own mistakes in 20 lines of code and you are using like OpenSSL or something which is just hundreds of thousands of lines where you cannot check if there is a bug or not. And heartbleed bug was a very good example for this scenario. So I suggest you, what you can do is as follows: just print everything step by step instead of doing this there's for loops for 100 keys and many plain text. Just do it for one key and for one plain text, and print every step on the screen and check by hand if what you want to do is correctly performed. Okay, you have to find it yourself. There's no way of otherwise doing it. So if you wrote your code in C, most probably there is maybe you are trying to reach an array value which you don't have access to or something. So I think it is easier to find the mistake in C when you are printing every step on the screen. And if you are using a Python code, I think some of you are making a mistake when you are converting your integers into hexadecimal notation and so on. So maybe you have to print all of these steps and see if you are doing it correctly. But other than that, I don't have any other suggestions. Maybe again, you have to print everything on screen and check if it is really working correctly. Some of you store all of the plain text they generated and even submitted in the homework, but I told you before, you don't need to store any of the plain text. If you're doing this, then this is a problem, because most probably you are writing it on the hard drive and maybe reading back, so this will cause a slowdown. There's no need to do that. And another point I need to make is, why are we performing this experiment for 100 keys and not just do it for one key? As you can see in these results, sometimes you might be lucky or unlucky. For instance, if you chose this key and perform the experiment on this one, the result will be 8, and this means that the probability is not as good as you expected. Or maybe you just hit a good key here and your counter is really high, and you say that, okay, the probability is really high, so it is, in practice, it is better, a lot better than the theoretical value. But this is not the case. So in order to show that we are not performing the experiment on a weak key, we are just randomly choosing 100 keys and they calculate the average of them, so that to see how it behaves for any key. Okay, this is why we are doing this. One key might give you a wrong result. That is the point. Again, if you go back to our results, as you can see, finally we obtained 2 to the minus 17.9, and in theory it was 2 to the minus 18. So the difference is not that big, so we have a marginal improvement here. So I mean, if you're writing a paper, you say that, okay, we are gaining something like 2 to the 0.1. You can use it, but in this case it doesn't help you much, so it is not that important. Okay, so in order to conclude, if your n is large, like 2 to the 22 or something higher like here, and if you still cannot get the p probability something like this, close to these numbers, then this means that you have an implementation error. It might be on your implementation of present, it might be on the implementation of the use of random numbers. So look at the random number generator, but maybe it is just an implementation error. Maybe if you're, for instance, using counters, maybe you forget to initialize them to 0 or something. So just check where you're making an error. And you cannot move on to the next homework without correcting this. I mean, we won't be directly using this code in our second homework, but still, in order to understand everything, I want you to correctly finish this homework. So, I mean, our homeworks, the grades are announced and everything's finished, but I'm giving you some time to correct your homework. So this way, when I give you the second homework, you can do it in a correct way. So I'm delaying the announcement of the second homework for a week, let's say, so that you can correct your mistakes and be ready for the second homework. And second thing is the optimization. Some of you maybe chose the n very small like this because your implementation was really slow. But a good implementation, for instance, in my implementation where I used 2 to the 22 data here, like this, it took less than 4 minutes on my laptop. So pay attention to your implementation for optimization, because you can really make it faster if you want to. I noticed that one of the students were printing every ciphertext on the screen, but if you do that, printing on the screen takes more time than performing the operation, so your CPU would work with 1% or something, so don't do that kind of mistakes. Okay, pay attention to optimization. So I think that will be all. So I'm delaying the second homework, so I suggest you to try to find your own mistakes and obtain these numbers, because some of you obtain numbers like -12 or -20 or something. So, but a good implementation should be a number close to this, -17.9 or something, or 88 or this kind of numbers. So again, if you wanted to know how can I know which n should I use, while performing the experiment, you could easily plot this graph by yourself and see if you are converging to some place. Okay, so this was the thing you should be doing initially. But again, as you can see, I already did it for you. And after 2 to the 20, we are observing that we are converging someplace. Okay, close to this number. Okay, that will be all.